Radar, short for radio detection and ranging, is a sensing technology that works by transmitting pulses of electromagnetic energy, specifically radio waves, into the surrounding environment and listening for the echoes that return. Fundamentally, every radar system is both a transmitter and a receiver. By measuring how long those reflected radio waves take to return and the direction from which they arrive, radar can determine the location of distant objects, often revealing targets far beyond the range of human vision. Although radar is often compared to sonar, a better analogy is an invisible flashlight. A radar antenna transmits focused pulses of radio energy, much like shining a powerful beam of light across the sky. When that energy strikes an object, a small portion reflects back to the radar, revealing the object's direction, distance, and sometimes its speed. Understanding radar this way also makes radar malfunction and deception much easier to understand. Just as visible light can be reflected, absorbed, scattered, or redirected, so can radio waves. The science is different from ordinary light only in wavelength, not in the underlying physics. Today, radar helps meteorologists track severe storms, allows air traffic controllers to safely manage thousands of flights, guides ships through poor visibility, supports scientific research, maps the surfaces of planets and asteroids, and even helps autonomous vehicles perceive their surroundings. But perhaps its most consequential application has been in military warfare, where detecting the adversary before being detected often meant the difference between victory and defeat. When radar first emerged during the 1930s, it fundamentally changed warfare. For the first time, military forces could detect aircraft beyond visual range, monitor large areas of airspace, and provide early warning of approaching threats, using nothing more than reflected radio waves. Radar was revolutionary, an invisible eye capable of seeing through darkness, clouds, and poor weather. But the scientists and engineers who developed radar understood something equally important from the very beginning. Radar was not magic. It was a scientific instrument built upon the predictable behavior of radio waves. And if radio waves could be transmitted, reflected, and measured, they could also be manipulated. Almost as soon as practical radar systems appeared, researchers began developing manipulation tactics. This marked the beginning of radar deception and ultimately the broader field of electronic warfare. Radar and radar deception have evolved together in a continuous technological competition. Every improvement in radar has encouraged new methods of defeating it. In turn, those new countermeasures have driven engineers to develop even more capable radar systems. For nearly a century, this cycle has continued without interruption and continues to this day. The animations shown here are intentionally simplified conceptual illustrations designed to explain these principles in an easy-to-understand way. Real-world electronic warfare systems are often far more sophisticated, integrating multiple sensors, transmitters, platforms, and techniques into coordinated operations. But regardless of their complexity, the underlying principles remain the same. One of the earliest and simplest examples of radar deception was Chaff. During the Second World War, military aircraft began releasing thousands of small metallic strips, cut to carefully calculated lengths. These lightweight pieces of metal reflected radar energy extremely well, creating large clouds of false echoes on enemy radar displays. Instead of seeing a single aircraft, radar operators might suddenly see dozens or even hundreds of confusing returns spread across their screens. Remarkably, both Allied and Axis scientists developed this idea independently, recognizing almost immediately that radar's greatest strength could also become one of its greatest vulnerabilities. Some approaches attempted to hide an aircraft from radar entirely by reducing the amount of radio energy reflected back toward the radar. This concept eventually led to what we now know as low observable or stealth technology. Rather than creating false targets, stealth attempts to reduce the strength of the true radar return, making an aircraft significantly more difficult to detect or track. It should also be noted that not every object reflects radar energy equally. Some materials and shapes are naturally far less observable to radar than others, and an object intentionally constructed from low reflectivity materials such as certain plastics, fabrics, or composites, may have inherently low observability before any dedicated stealth technologies are even applied. Modern stealth aircraft build upon these principles through carefully engineered shaping, aligned edges, internal weapons carriage, radar-absorbing materials and coatings, shielded engine inlets and exhausts, and meticulous attention to surface details such as panel gaps and fasteners. Beyond these well-documented techniques, there has long been public speculation and documented research into more advanced concepts such as plasma stealth, ionized air, and electrically energized leading edges, which seek to reduce or alter radar reflections by manipulating the electromagnetic properties of the air surrounding the aircraft. While no operational aircraft is publicly known to employ these techniques, research has generally focused on treating only the aircraft's most radar-reflective regions, such as leading edges and engine inlets, rather than attempting to surround the entire aircraft with plasma. Other techniques focus not on hiding, but on overwhelming the radar itself. Powerful transmitters could broadcast radio energy directly toward enemy radar systems, masking genuine echoes beneath intentionally generated noise. This practice became known as radar jamming. As electronic technology improved, engineers developed increasingly sophisticated techniques capable of doing much more than simply creating interference. Instead of overwhelming a radar with noise, modern electronic warfare systems can manipulate radar signals with remarkable precision. By carefully receiving, processing, delaying, modifying, and retransmitting radar energy, electronic systems can alter what a radar operator believes they are observing. Depending upon the technique employed, electronic deception may attempt to change the apparent position of a target, alter its apparent speed, generate additional false targets, disguise the size of an object, or complicate an operator's ability to distinguish genuine returns from deceptive ones. The specific techniques have become increasingly sophisticated over the decades, often combining several modalities in an orchestra of deception. But the underlying principle has remained remarkably consistent. Manipulate the radar and operator's perception, not by violating physics, but by exploiting physics. Electronic warfare relies on real engineering, real equipment, and real physical objects. Whether it's chaff, decoys, antennas, transmitters, or the platforms carrying them, the deception lies not in creating something from nothing, but in influencing what the radar system perceives. As radar technology has evolved from the earliest mechanical systems to today's sophisticated digital phased array radars, electronic warfare has advanced alongside it. Nearly every major improvement in radar has been met by new methods of electronic attack, protection, and deception. The contest between seeing and deceiving has existed since the earliest days of radar, and it continues today. Thank you for watching. I hope this reconstruction has helped present the available evidence in a clear and engaging way. If you enjoyed this video, please consider liking, subscribing, and sharing it with others who have an interest in aviation, military history, and unexplained phenomena.